Good morning, everybody. I'm starting a minute earlier, so to give Shahal wait the whole full time. My name is Moti Heiblum. I'm going to chair the first two talks of the day. I'm also, if you probably know that we spent 2 years to organize together with Amnon and Aharony with ups and down. And I'm happy to have you here, but maybe we'll talk about it at the end of the day. So I'm happy to invite Shahal Ilani. You can read yourself the title. I just add a word that I regard Shahal as my academic grandson because my first PhD student was Amir Yacobi, who is now in Harvard. I'm sure that this name is known for everybody, so I'm very proud of him. And I'm proud also of my grandson. He was the first student of Amir Yacobi. Okay, Shahal.
Okay, good morning, everyone. It's good to be here, and thanks, Moti, for this warm introduction. Microphone is no. I have a special microphone. Good. So today I decided to talk about kind of a different subject that than I think what's most of the action now, where I'm going to talk about a question which is a textbook question, is where is resistance coming from, electronic resistance. And I'm going to touch on the fundamentals of resistance, and I'm going to show you an experiment. This is recently published work that asks this question: what's the bound on resistance, electronic resistance, and can interaction between electrons, what we call electron hydrodynamics, eliminate or break these bounds, and how much? Okay? So what we do in my lab is our works that typically involved imaging, seeing pictures of electrons, and we typically look on interacting phases of matter, Wigner crystal, magic angle graphene, all the Mott insulators, and so on. And we have been studying also electron hydrodynamics, and for me, the biggest question in the field that remain is what is it good for? Can they do something that we don't learn in textbooks? So that's kind of the subject of this work. And let's see, so this is a remote. There is another remote here. Let's see. Okay, so when we learn in textbooks why electrons have resistance, we all know that resistance is backscattering. Electrons go in a material, and they have multiple reasons to get backscattered, either by impurities in the materials, edges in devices, phonons, what have you. Okay, but if I ask a question, what happens if I make the perfect material, eliminate all this, would we have no resistance? If electron that I launch from one contact always make it to the other side, would we have no resistance? And I guess that you all know that the answer is no, because Landauer taught us that even in the perfect case, there is always a finite conductance capability of a material. So what we have is quantum channels. Each one of them carries E squared over H of conductance. And then a given width channel has a limited resistance, which we call Landauer-Sharvin resistance. Now, electrons do not scatter. So how can we have resistance? Where is this resistance? Okay, and this is something that Sharvin really sharpened. This resistance has to happen at the contacts. This is sometimes called, because of this Sharvin resistance, because this is where the electrons realize that they have limited phase space, limited number of channels, where they go into the channel. So if we could plot the resistance as function of position, half of the Sharvin resistance would drop on one contact and half on the other. All right. Now, this is a fundamental question, of course, But it's also of very practical importance because, as you know, computers are making chips smaller and smaller, Moore's law, and sometimes you hear that Moore's law is dead because we cannot make things smaller. It's not really true. Scaling down is still continuous. The reason that we are blocked with computer is actually that we have a problem of heating. Now the bottleneck is heating. That happens in the contacts. And the ultimate limits for that is the Landauer-Sharvin limit, which means that even if we make our contact as specific as possible, we will still have heating because of this. So it's important to ask, can we break this limit? Can going to electron hydrodynamics change the rules of the game here? Okay. Now, in most materials in the world, there are enough impurities that electrons are basically behaving like this. They behave like independent particles. But more and more people are making materials that are clean enough such that electrons collide more often with their fellow electrons rather with impurities or lattice imperfection. And once you go into this regime, electrons behave more like a collective liquid, which we could, and this is the field we call electron hydrodynamics. There have been a lot of work in the last few years about this and various aspects of that. And one specifically interesting work in our context is a work that measured what's the conductance of hydrodynamic electrons through a constriction like that. And what was seen is that they can conduct slightly better than the Landauer-Sharvin limit. And theoretically, this was explained by electrons avoiding the walls, lubricating these walls of this constriction. And this is a nice hint that something interesting can happen with hydrodynamic electrons. And what I want to ask today is, what happens if we have no physical walls? Okay, what will happen? And how do we get no physical walls? This was a proposal by Gregory Falkovich from Weizmann. You make a device like this, which is called the Corbino disk device. Basically, electrons go from one contact here to another contact here, never face walls. And the question, what happens if these electrons are hydrodynamic?
How did you get rid of the contacts?
No. It's a disk, a compact disk, where you have one contact in the center, one contact at the edge, and electron flow from one contact to the other without meeting walls. Okay, that's the standard way of avoiding walls. And now let's ask what happens. And what Gregory Falkovich did when he did the Navier-Stokes solution of flow in this geometry, he got something weird, that electrons flow without electric field. At the beginning, it doesn't sound very weird, and it took me time while we were doing the experiment to understand that this observation actually has a deep connection to the question that I'm asking today, which is the Landauer-Sharvin limit of resistance. So one advantage of a geometry like this, a Corbino geometry, you see immediately there are no edges, whereas here we have edges. And it's good because in both these geometries, we have this Landauer-Sharvin limit, which is given by the number of quantum channels that can go from one side to the other. And this is limited by the narrowest part in the device. So in a channel, it's the width of the device. In this geometry, it's the circumference of the inner contact. Okay, this would limit the Landauer-Sharvin resistance in both cases. But now let's assume that we have the case where we don't have any scattering in the bulk. Every electron that we launch from one contact makes it to the other contact. Okay, where would this Landauer-Sharvin resistance be? So I showed you that in a channel, half of it is here, and half of that is there. Let me ask you, where do you expect this Landauer-Sharvin resistance to be here? Any guesses?
I would guess in the center, but if you are asking, the answer is probably the opposite.
Okay. Any other guesses?
Usually when you have Landauer-Sharvin, the interpretation is that there is relaxation in your bodies, and this is where the resistance comes from.
In your what?
In the reservoirs.
Okay.
So electrons come out with an unequilibrium distribution and they relax, and this is where we actually do the dissipation.
Okay.
It's in the reservoirs.
So in the reservoirs. Okay. Okay. So similar to this, something like that.
Yeah.
Any other guesses?
I would guess 50.
Half enough. Half here and half here. Okay. Okay. Already 3 different guesses. Any more? Okay. No one wants to guess. So this is something that you can, there is a theoretical prediction for that. And indeed, in the center contact, half of the Sharvin resistance should drop. But the other half, in fact, is not going to drop in the other contact. It's going to drop continuously along the bulk. Okay? So although there is no scattering in the bulk, there is going to be resistance in the bulk. Independent of the size. And why is it? I mean, in a second you will tell me that it's trivial, but let me show you what it is. Because I remind you, what is the Landauer-Sharvin resistance? It's the resistance because I have limited phase space, limited channels. Now think of how many channels I have in these geometries. In this geometry, the number of channels is fixed along the way. And electrons realize that they have a limited number of channels when they get in and when they get out. Okay? But in a Corbino, I have many, many channels outside, and as electron goes inside, it has less and less and less phase space. Okay? So it gradually understands that it has less phase space. It gradually pay this resistance, Landauer-Sharvin resistance. So we have an interesting case where resistance that until now we know exists always in the contacts of devices and so on. Now we have a device where we spread this resistance on the bulk. And it's also interesting because we can look on it with imaging experiments, okay, and ask questions about it. Oops, sorry.
You know, Shahal,
Yes?
resistance is energy loss. Counts time resistance. Counts square time resistance. Why do you have energy loss? Where does it go?
So it's a good question, but in ballistic case, you have this resistance, and the loss will happen at the contact. So what happens, ballistic flow is such that electrons, as they flow in the ballistic device, they become hotter and hotter and hotter, much higher than the local Fermi energy. But they realize that, it's like the cartoon figure that is flying off a mountain and realizing after a while that it's in the air and start falling. So the start falling, it happens at the contacts only. Okay, in the device, you don't lose energy in ballistic flow. Yeah. Right. But it happens in the contact. The energy loss happens in the contact. But what I'm plotting now is, okay, you'll see how we describe resistance and you'll see in a second. Okay, so but 1 second, let me finish this and then. The theory basically not only tells us that the half would be distributed like this, it actually gives a very clear formula, an arc sign, how it should be distributed. And in this context, if you now think of what I showed you of Falkovich prediction, now you can understand why it's very surprising, because what it tells you is that this very fundamental resistance is eliminated. We get that inside here, the bulk, the resistive drop would be 0 for hydrodynamic electron. And what this means is that in this geometry, we eliminated half of the Landauer-Sharvin resistance, okay? Which typically we are said we cannot. You know, that's the limit that ballistic electrons have. And so half is really good, you know, but the question is, can we do better than this? Why are we stuck with the half? The reason that we are stuck with the half is because we force electrons to very abruptly go from a contact to a conductor with few channels. And at least theoretically, we can avoid it. You can imagine a geometry that looks like this, where we have one contact, electron flow here. Here, we don't force them to go out. We just continue this conductor, let them expand out, and measure the resistance, measure the current coming out here. And you can ask, here I have a very, very narrow channel. What would be the resistance between these two? Okay? Would it be limited by the bottleneck, as we typically do? And we extended it in a theory work to a more generic geometry, wormhole-like geometry like this. So it's the same question. Ask, what's the resistance between this contact, electron going through a pinhole? Okay? And no walls in this geometry. And the answer is really interesting. So you basically think of non-interacting electrons going along geodesics here. So some of them can have lines that can make it through, and some of them just basically reflect back. And in a more abstract sense, you can think of channels, quantum channels. Some of them are propagating through, and some of them terminate, classically, semi-classically terminate and go back. And what you see is that electrons that are in channels that do not terminate conduct, and they give conductance and don't give voltage drop, so they don't contribute to resistance. But these other electrons are hitting this point, go back. They don't contribute to current, but they contribute resistance. So all these are going through. These are the privileged one. These come and come back. And what this causes is a quantum traffic jam, which means that there would be resistance here and here. And this resistance, if these are ballistic electrons, no matter how you shape this trumpet here, how adiabatic you do it and so on, it would always be the Sharvin resistance of how many channels you have here. Okay? And why is it relevant? Because in a computer, this is what happens billion times every second. Because each time you go from copper wire to a transistor, which have few modes, to a copper wire, even if everything is perfect, you have to pay this resistance. So this is like the bound on heating. Okay? Now, the thing is, okay, so you say, how can we break this? You know, maybe you say, okay, if it's superconductor, maybe if electrons attract each other, they can go through better. But interesting thing is that the electrons solve it the Israeli way, by repelling each other, by scattering against each other. So it turns out that it's, even if you scatter electrons of each other, what happens is that before a channel gets terminated, the electron is getting pushed to other conducting channels. And that's, I'm going to show you soon the experiment. But the theoretical result shows you that what happens is that if you have interaction that can operate on the length scale where these channels are closing up, then what you can is you can squeeze more electrons than the Landauer limit allows you through these channels. You can basically, and the theory tells you that you can squeeze as much as you want. Okay? In principle, there should be zero resistance to this device if it's gradual enough and electrons are hydrodynamic. Okay. And what's nice about Corby, and what you can see theoretically is that the resistance that you pay ballistically is always proportional. Whenever you change the number of modes, so there is a first derivative, you pay resistance. But hydrodynamically, you don't pay this. You pay only when there is second derivative. And what's nice about Corbino is that the number of modes increases linearly with distance. So hydrodynamically, you should get zero resistance. That's like the most ideal case of changing the number of channels. So you know, you can be in a state where we measure that hydrodynamic electrons have zero resistance. Okay, so I kind of finished the theory. I want now to talk about experiment of measuring resistance. So if anyone has questions about this now, it's a good time.
So when you mentioned at the beginning...
Microphone.
So when you mentioned hydrodynamics,
yes,
there is no friction, right? There is no...
There is.
So if I write... I don't write Navier-Stokes equation.
You write Navier. Yeah, you do.
And there is viscosity?
There is viscosity, yes. I mean, electrons, through their interaction, transfer momentum. There is diffusion of momentum, yes. Okay. You know, another way to think of Corbino, like if you write Navier-Stokes equation for Corbino, you see that the viscosity term comes before a Laplacian, which means that you pay viscosity if you have you can write the Laplacian as a curl of vorticity or gradient of vorticity. Okay, so only then would electrons feel the viscosity. And in circular flow, that's something that Falkovich understood. There is no vorticity and definitely no gradient of vorticity. This is why you don't pay the viscosity of the electrons. Although, so what I'm saying is that there would be no resistance even if the electronic fluid has viscosity because of this geometry. Yes?
Does the current limit this funneling efficiency of the...
Is following what?
The funneling.
Funneling, yes.
Collecting.
Yeah.
Is there any... The current limit that funneling efficiency, For example, if you think of water putting in this funnel, there is a speed limit, right?
Right. I mean, there can be limits that can come from the nonlinear terms, for example. But basically what you want to do, if you want to get zero resistance, is to funnel as slowly as possible. You know, kind of the theory shows something really bizarre as compared to what we learn. Like typically we learn that in Ohm's law, we have a device. If we make it longer, resistance increases like L, right? For ballistic electron, if we make it longer, it doesn't change. In the hydrodynamic case, we get that it goes like 1 over L. You make it longer, you get less resistance, okay? Because you can funnel slower as compared to electron-electron interaction. So this is kind of a weird result. But now let's go to experiment. So we want to measure how resistance is distributed, yes?
So what happens if you apply magnetic field? You have a good geometry.
You'll see in a second. In the experiment, you'll see.
Okay.
Okay. So we want to measure how resistance is distributed, and what we use is a tool that we developed a few years back in my lab, which is a very sensitive local electrometer that is based on a carbon nanotube at the edge of a scanning probe. At low temperature, this nanotube becomes a quantum dot, and if we measure the current through the nanotube from one contact to the other, it follows the Coulomb blockade phenomena, namely current oscillates very sharply with each induced electron on this quantum dot, which makes it a very, very sensitive detector. It means that if we are sitting in a place where current changes very abruptly with a local electrostatic potential, we can measure electrostatic potential much better than that induced by a charge of an electron, which is a full period here. And in fact, we can see with this technique about 10 to the minus 5, 10 to the minus 6 of the electronic charge per square root hertz, which means that we can easily see single electrons with this technique, even when they are buried beneath an insulating substrate, because what we are doing with the technique, we are sensing the electric field that emanate from them. We don't need to pass current like in STM, okay? This technique is good for different kind of experiments. So you can measure equilibrium properties of electrons. For example, how do they organize, what kind of phases they organize in real space, or what their thermodynamic properties like compressibility and entropy. And we did it on imaging Wigner crystals, showing that electrons can attract each other, works on magic angle graphene. But today I want to talk about a different measurement, which is measuring out of equilibrium, basically doing the scanning equivalent of transport experiment, okay? So I'll talk briefly about the work that first got the first images that electrons flow like liquid, and then this really recent work about flow in a corbino like that. So how do you typically measure resistance? You make a hole bar, you flow current, and you put voltage probes. You measure how much voltage drops. If you have magnetic field, you can measure also hole voltage, right? This is really nice. We know it's a super powerful technique, but it also has its limitation. One limitation is that you know the voltage only at discrete points, and they have to be along the perimeter. You don't know what's happening in the bud. But the other limitation is that the contacts that you put might be invasive to the flow that you are trying to measure. And the most extreme case is that of the corbino, because you can imagine that we want to have the flow from here to here, but if we want to do this measurement with these two probes inside, they would interfere with the flow. So this is not good. We cannot do it in transport. Luckily, what we do is that we don't need this contact. What we do is we get rid of the contact. We still pass the current, but then we use our local electrostatic detector to image how the potential looks when the electrons are flowing. So for example, what you see here is that the potential here is the equal line potential. It drops from one contact to the other, as you would expect. You can see that there is a small angle because this is a magnetic field. And if I increase magnetic field, you see how the potential rotates. And this is kind of the textbook demonstration of whole voltage in a device. Okay. So quickly, what is it good for? If we have a way to image how voltage is in a nanometric device, we can ask questions of like, where is the resistance? And graphene is really good for it because graphene we can take between different regimes of flow. So for example, if we are in the Dirac point, graphene is diffusive. And if we image how the potential drops in a channel, we see it's very trivial. It drops linearly. Like if you take fluke and measure the potential at different points along a resistor. That's what diffusive resistors do. But, slightly more interesting is if we take graphene into the ballistic regime, right? And we discussed it. Where is the resistance in a ballistic regime? And if we do this measurement, we can really see that the potential doesn't drop along the device, but it drops near the contacts. And this is the Sharvin resistance dropping at the contact. So we can really see that. So this is measurement of voltage. But sometimes you do want to measure current density, local current density. It's interesting. And we cannot measure current. But it turns out that we have a trick to do that. And this is to add a small magnetic field that doesn't influence the physics. But what it does is that at every place that we have current in the sample, there must be also a local hole voltage, just across the current. So if we can measure the hole voltage, we can translate it to the local current. So what we did is to use this technique to measure how the current is distributed along a channel like this. And what we saw is that at low temperature, the current is kind of homogeneously distributed along a channel like that, which is what you would expect if electrons are ballistic and spread the information homogeneously along the channel. But the interesting part is if you heat up the system, you open phase space for electrons to interact with one another. And when we do the same measurement there, we see that the current is actually distributed in a parabolic way in the channel. And if you did any course in hydrodynamics in your past, this might look familiar. This is what's called Poissy flow. This is how water flows through pipes. Okay, they have friction on the edges, and they're flowing mostly in this. So this is like a very direct visualization that electrons are behaving like a hydrodynamic fluid.
Is it clear that in a ballistic case there will be local relation between the voltage and the current?
No. So this is now a second order for advanced thing. It turns out that there is no local relation, and it turns out that it actually helps us that we are measuring the whole voltage and not the current density, because if you measure the current, but this is for advanced, I can tell you, but that's what actually saved us and made it possible. Okay, but now I want to talk about flow in Corbino. Okay, so it's the same thing. This is the device now. It's basically an uninterrupted disk of graphene, very, very clean graphene, no defects, very long mean-3 path, 40 microns. Contact in the center, ring contact outside. We put it in a sandwich of HBN, connect from the top such that we don't interrupt the disk. We run current from the central contact to the outer contact, and we use the nanotube single electron transistor to image how the potential drops. This is an optical image. It's pretty large scale, but our mean-3 path is large, so we are fine. And this is what we see when we image the potential when electrons are flowing. And here you see the same thing, but we divide by the total current, so it gives us something in units of resistance. And the way you want to think about it is like, here is the 0, and this is how we accumulate resistance as we start from the outer contact to the inner contact. The integral of this from here to here is just the 2-probe resistance you will measure in transport.
It's a single Corbino, not the funnel.
Single Corbino. We don't know how to make funnel. This is only in theory world. So it's beautiful. Yeah, we're actually thinking of how to do that. But yeah, in real world you can do just the half wormhole. Corbino is a half wormhole. Okay, we can gain this. So this is this. You see, we have really nice angular symmetry, which means that we can average along the angular axis and just look on the profile, which is the important thing we want to do. So this is the profile. You see that, and this is the resistance plot in units of the Sharvin resistance. Okay, you see that we start here flat, then there is a sharp increase, then it gradually increased. There is another sharp increase here, and it stabilized here. So what are these 2 steps? These are actually coming from resistances in the contact, and we can understand it, know exactly how they're smeared by the point spread function of this, and we can eliminate it because we want to subtract it and want to focus on what's happening in the bulk. That's the question that I want to ask today.
How do you define resistance scale micron? How is resistance translate?
So it's simple. It's voltage drop divided by the current. Just like you do it in transport, right? You'll have a low bar.
So it's the delta V over I.
Yeah, exactly. So this is after that, and this is what we get in the bulk. And you can see very nicely that first the scale is what you would expect. Half of the Sharvin resistance is dropping in the bulk. It's rising very continuously. And the most important thing is that if we compare it to the theoretical prediction that I showed you before, this is it. Okay? No free parameters. This is the arcsine formula. You see that we are pretty close. So what you see here is that a device that doesn't have any scattering has resistance in its bulk because of the channels getting close. Now, scattering, there is tiny, tiny scattering, and the scattering is, in fact, explaining the difference between these two. So if we add a small ohmic term, we can explain it completely. But the main source of resistance here is this half Landauer-Sharvin resistance, okay, that is spread now in the bulk. And now, I'm cutting a bit short the details. Now we want to see what happens if these are ballistic electrons at low temperature. Now we want to see what happens if we turn them into hydrodynamic electrons. So what we do, we warm up the experiment and measure it at larger temperature. At larger temperature, two things happen. Electrons scatter more off electrons, which is good for us because this is momentum conserving scattering that preserve. This is why we get hydrodynamic. But electrons scatters more off phonons, okay? And this also happens. I don't show it here, but we can. The contribution is not very large, and we can eliminate it. So I'm going to show you what happens after we can exactly measure it and eliminate it. So I'm going to show you what happens if we eliminate the phonons and look only on the resistance that remains. Yes? Yes, good, good. So this is what we see as function of temperature. At low temperature, what I showed you is that we have the distributed Landauer-Sharvin resistance, half. And then as we increase the temperature, we see that it drops more and more and more. At the highest temperature, we get that it's completely flat, no resistance along the bulk of this. And this is a comparison with a Boltzmann calculation of the same thing with decreasing level or more and more interaction. So shorter and shorter electron means scattering 3 paths. And you see that they are very similar, specifically in two aspects. You can see that in the center, there is still what we call the Stokes resistance, which is the resistance that happens on a length scale, which is the electron-electron interaction length. So basically, when electrons go from the contact into the device, it takes it a distance of electron-electron interaction length to learn that it's living in a liquid, right? Before that, it thinks that it lives in the world for itself. It thinks that it's ballistic. So up to this length, you're still paying, the Sharvin that you should have paid. But after this length, where the hydrodynamics takes on, it's basically perfect. So here you pay the Stokes resistance, and here we have perfectly flat resistance. Okay, so this is one important result. And I want to end now with what happened. Someone asked me at magnetic field. Okay, so why you put magnetic field? In a sense, magnetic field is going to swirl our electron. And we have a nice geometry, no boundary. So it's going to be like a washing machine for electrons, right? We can measure things on the liquid that are nicely measured with magnetic field, okay? And especially, it would be some kind of a viscosometer for us. So this is the measurement with magnetic field, okay? Now we did not remove phonon resistance, so even at zero magnetic field, we have some logarithmic term here. But the important thing that I want you to observe is that even if we add tiny magnetic field, here 30 millitesla, the resistance in the bulk increases a lot, almost by factor of 2. Which is unusual. The system doesn't have large magnetoresistance. And if you have sharp eye, you can see that it increases more. The slope here is sharper than in the edges. So if I plot the derivative, I see that there is larger increase in the center than in the edges. Okay? Now, why do we have why magnetic field makes this much more resistive? It's not the magnetoresistance of the material. It's because of the geometry. You have to remember, if you taught some transport transport course recently, that Corbino has a different symmetry than whole bar. In a whole bar, the boundary condition is that current is not allowed to go perpendicular. In a Corbino, the symmetry is that you are not allowed to have a circumferential field like that. Okay, which means that here, when we do this two-probe measurement, we measure the rho x6, and here we measure the sigma x6, the inverse conductivity. At zero magnetic field, they are the same, so it doesn't matter. But if you put magnetic field, there is this extra Hall voltage term that we measure. So this is what gives us this increased resistance, because electrons are going like this, and we measure the Hall voltage of electrons rotating, of the current that goes inside, okay? And in fact, you know, by the magnetic field dependence, we can extract independently this and that. So we can plot how the Hall voltage depends on position. And we see something nice. We see that the Hall angle is basically rising up, reaching the value which is the classical value that we learn in the literature of a Hall angle that compensates Lorentz force against electric Hall field. But the rise to this is very, very slow. You know, this build-up length is much larger than our resolution, which is given by the black thing. So something happens. Something happened. Electrons do not reach the normal classical Hall resistance, Hall angle, immediately. And in fact, we see it also when we take two-dimensional images of this washing machine. So here it's the Hall angle as function of position. Here they establish the classical Hall angle, but there is a build-up length here. Okay? And it took us some time to understand, but we understood at the end that the reason for that is that the boundary conditions of electron leaving a contact is that they always have to leave the contact perpendicular to the contact. So when they leave a contact, they cannot have a Hall angle. Okay? And as they flow in the channel, they acquire this Hall angle. Okay, so there is some build-up length to that, and it turns out that if electrons are hydrodynamic, the length is none of the, microscopic lengths in the problem. It's not the electron-electron interaction length. It's not the inelastic, the elastic scattering length. It's the geometrical mean between them, which is called the Gurji length. This is the most basic quantity in hydrodynamic theory, and in fact, we can see that this build-up length is exactly the Gurji length. So this is the first time we can image this basic property of electron hydrodynamic seat directly by eye. Okay, this emergent length of the theory of hydrodynamics. So with this, I'm ending. I showed you an experiment that used local imaging of potentials to ask where is the resistance, and I showed you 3 results along the way on Corbino. I showed you first that we can image the Landauer-Sharvin resistance distributed in a bulk. It's a geometrical resistance because of channeling closing, not because of any scattering. I showed you then that if we heat up, we make the liquid hydrodynamic, we can eliminate this. And lastly, I showed you that with magnetic field, we have a nice viscosometer, and we see a boundary layer that reveals this fundamental length, the Gurji length of hydrodynamic electrons. So with this, I want to end. Thank you for your attention.
We have only a few minutes.
Yes, thank you. Thank you very much for your very nice talk. And I was curious about with this magnetic field, can you think of the transverse conductivity, and have you tried to measure it?
Transverse conductivity. So for now, our technique is measuring only voltages. It doesn't measure current. So we cannot see directly the current, the azimuthal current. Okay? But if we have a way to measure current, then we'll do that. And we are trying, you know, we have now different techniques that we are developing, and we believe that we'll be able to measure both voltage and current, and then we can do everything.
Beautiful.
Simple enough?
I could follow. But I do have a question. So what's the Reynolds number of your electron fluid, and can you get turbulent electron fluid?
Yes. So unfortunately, in all this field, the Reynolds number are still low numbers, okay, so of the order of 1. Okay, it's related to the collision length versus the device length, and to the drift velocity over the Fermi velocity. And you know, these numbers cancel themselves and it's about 1. If you want turbulent, you really need higher numbers. But you know, we're thinking whether in really highly nonlinear parameter regime of the flow, you could be there, and then it would be interesting. Yeah.
Okay, so are you assuming the frictionless substrate under the context? What is the effect of the
frictionless in the bulk of the device or in the contact?
Yeah, under the context.
You mean like at the bulk from the HBN if there is a scattering? Mm-hmm. So this we can measure, right? You see the effect of scattering by impurity is the difference between this and that. Okay, so this is really, really tiny. So our device's diameter, radius is 9 microns, but the mean 3 path is 40 microns in these graphene devices. They are super clean. So the scattering is very rare. So it's not a big contribution.
I said there are more questions. Maybe the next speaker should set it up and then get another question or two in a minute. Next speaker. John? Okay, so you can set it up and share your short question.
Yes, so in the ballistic case where you show the resistance distributed along the Corbino disk, but where is the dissipation? Where is
dissipation is in the contact. So again, you know.
So although you have a resistance or voltage drop in the sample, the dissipation is still.
I mean, if you think about it.
How it's distributed between the two contacts, equally or not equally?
I think it would be equally. I didn't think about it. But you know, in a way, what I want to say is that you think of ballistic as something that doesn't waste energy. There is no dissipation. But it's not true, because in ballistic flow, as I mentioned when Moti asked, like electrons go as much as out of equilibrium during their traversing in the device as possible. In fact, you know, what electron hydrodynamic does is that it equilibrates the electrons at shorter length scale. Okay, so each time an electron gets hit by electrons, it kind of thermalizes to the local or goes to the local energy. So it's more in equilibrium during the way. So the way you want to think of ballistic flow is having an LEE, the electron-electron interaction length, equal to the size of the device. So it's the largest non-equilibrium equilibration distance that you go. This is why it's the worst in terms of the resistance that you pay.
We have to stop now.
Yeah.
Okay. Please.
Sorry.
Sorry.